What's up, guys? Welcome to another episode of CCT. Today I just wanted to go through a problem that I've never done before, and it just looked interesting. So, merging two binary trees. That's what I'll try to do today. Yeah, let's jump right into it. Given two binary trees, imagine that when you put one of them to cover the other, some nodes of the two trees are overlapped while others are not. Okay, you need to merge them into a new binary tree. The merge rule is if two nodes overlap, then the sum node value appears. Oh, otherwise the not null will be used for that. Okay. So it's kind of, this is cool. I can see why it has so many likes up here. Basically, if you put this tree on top of this tree, you see like the 2 and the 1 are going to overlap, so they sum to be 3, and the 1 and the 3 are going to make 4. And then here, like, this tree has nothing here, but tree 1 has 5, so 5 plus null or whatever is 5. Okay. Interesting. Okay, so I almost want to traverse or like recursively both trees at the same time. And this recursive function makes sense. It could take in both roots and we could go both left at the same time. Okay, so here's the idea. If they both have a number, you can... Oh yeah, we need like a resulting tree. Maybe we will use a helper only because we need a result. Okay, so let's just say if they both have a value, sum them. Wait a second. This is supposed to return the tree or what? Given two need to merge them to the sum node, otherwise not the merging process. Yeah, I would assume we need to return it. So usually how this works is when we're like returning a tree, we usually start with like, yeah, we're probably gonna need a helper, and then like when we do the recursive call like this, we have like root right gets this. So actually this we will need a helper because this isn't enough. We need to put the like current root of our new tree in along with these parameters. But anyway, if they do both have values, then we sum them, and then we sum them. We're going to need to then create the node, then recursively add to the rest of the tree, and then return the node, the like root node. So does that make sense? Like, this is part of the idea, a big idea with binary tree problems, is you like can create something, but then you need to do stuff on the left and the right side, and then when all of that stuff is done, then you can return like the root node. So I think things will make more sense when I write it out. So I'm very into this style of nested functions. Yeah. Okay. So we have tree. Let's actually do root tree 1 and tree. Actually. Res root root 1, root 2. Okay, yeah, that makes the most sense to me. So, merging trees, so we have to see. Yep, okay. So, I kind of just want to do the main part of this function first. So it's gonna basically be res root left gets the helper. Alright, wait, yeah. Gets the helper that takes in oh, wait a second. Oh, we don't actually need this. We just need to be returning this. Actually, yeah, this is actually enough. This is, yep, this is enough. Okay, let's actually construct the tree node. So, tree node root. I think that's how you do. Oh, it takes in the value. Let's just do t1 val. For now, let's assume they just both have values right now, or that they're both not null right now. Okay, so we have our root, and then we need to do root. Oh yeah, dot left is gonna get the merged trees of the left side. And then root right is gonna get the merged trees of the right side. Okay, so it's kind of like we created this node and we did stuff to the left, and we're just going to take this recursive leap of faith that this is going to create the left tree and this is going to create the right tree, and then we can return the root here. Okay, so actually, so we definitely need cases, but this is a rough sketch of what it could be. Yeah. So the first thing that needs to be done. Yeah, so this is actually just a case if T1 and T2. I don't even think these cases can really overlap because each line needs to be slightly different. Okay, well, I'll think about that in a second, but if just T1, because we know it can't be T2 with, or, actually, yeah, and not T2, then that means, so this is if the, yeah, we'll stop it here. This is if the T1 actually has something, but the T2 doesn't. So notice that we're just checking like kind of the roots. It's not like we're at 3 here and we're checking, oh, does it have a left or a right? We're not going off of that. We're gonna wait until, okay, like this 3 exists, so then let's go to the left here. And then in that case, it's gonna see the 5 is there, sorry. And then in the next case, when it goes left, it'll see that there's nothing there. And then that's where like the base case is. Note, like I'm trying to say the base case isn't, like it's simpler to write the base case when you actually traverse to the null node before and not when you're at the leaf node. You know, just let it go to the null node, and that's usually a more elegant solution. Okay, so anyway, so T1 has something, but T2 doesn't, so this we cannot do. So we're just going to write... Does that know? Is it just null? I thought it was null pointer. Well, if T2 isn't anything, I guess we might as well just do that. And if T2 isn't anything, then we don't have that either. Okay. Else if not T1 and T2, then we're going to have a similar case to this. I'm still trying to see if I... This is probably not the cleanest way to do it. I'm thinking like I could calculate... I don't know. I mean, actually, this is quite readable, to be honest. And sometimes, even if it takes more lines of code, I would definitely choose readability, even if it takes more lines of code. Okay. So that's good. And then the last case is that they're both null pointer. Close one. So if they're both null pointer, then we should return a null pointer so that they... Oh, none. That's what it is. Huh. That's what it is in Python. Yeah, I feel more comfortable doing none here then. I mean, even though they should already technically be none, but that just looks better, I think. Okay, so yeah, that's the idea. Let's see if that runs. Huh? How do you declare in Python? Okay. Declaring instance of class in Python. Apparently I forgot that. How do you do that? Oh, it's... Oh, okay, I see. Can you not do it the other way? Sometimes I get confused between C++ and C. Interesting. Okay. So yeah, let's do it that way. So root... Oh, yeah, that makes sense. Because you can't even declare something in... You can't declare the type in Python, so that makes sense. I should remember that. That's how I can remember this. You can't declare types in Python. What's wrong here? Oh my god, pointer syntax. No. Okay, just give me a minute. Feel free to fast forward this. I don't have a very fast way to do this, so... Oh my god. You know, sometimes Python's a little more annoying than I remember. It has its annoying qualities. Okay, nice. So let's go over some test cases now. Okay, so... let's go with an empty tree like this. This is always a good case. Adding null and null. Okay, good. So we got something different. Interesting. So, So I outputted 2, 1. Oh my god, I just saw this here as being right. I don't know if that's... Yeah, I just kind of noticed that, like, why is the 1 also on the right side? So I thought about that, but... Okay, cool, that was it. Okay, and then another classic example that you always want to test is the null on null. It's a good one. Make sure it can handle that. It should just get to this one and then return none, I guess. Okay. Let me think. What else would be interesting? If they both had stuff in opposite direction. Yeah, I mean, this isn't actually that good of a test, but let's... I think it's worthy, like, to stick things. So let's do 1, 2, and then you need a null, and then 3, because that would be... The 3 would be... It would be like 1, 2, null, 3, null, or something. And then let's do 1, null, 2, is it capital N-U-L-L? Yeah, whatever. 2, then null, 3. Yeah, it probably is. If I'm not mistaken. Can you visualize this now? Ah, okay. Let me just cut that and let's go back. What was the issue before? Oh, it was all lowercase. Dang it. Okay, and this one, perfect. Let's run that. Okay, I'm satisfied now. That tree visualizer is pretty nice. Okay, let's submit it. See what we got. Why is that so slow? What? Oh. Maybe I can... I mean, an idea to speed it up is that if only one of the parts of the tree is valid, then what I could do is I can just make it equal to that side. So, for example, here, instead of this, what I could do, but then I would be pointing to the same object, and this is like, this is not a copied object. I don't know. Let's see what they say if I do this. If I just return T2 at this point, because T1 is nothing, and then over here I return... Like, I don't really agree with this solution, so hopefully they don't accept this one, but let's just run this first to see if they... I mean, they probably will. It's not... Yeah. Okay, let's see. Yep, okay. Much faster. I don't know if I agree with that, though. I mean, unless you're just trying to throw this out, throw the T1 and T2, but whatever you passed into there is like it's subject to being modified if you modify the resulting merged tree. Interesting how my space memory usage is so high. I don't, because I'm using a stack, I guess. Yeah, I'm not sure. All right, well, sometimes it's weird like that. So I think we'll leave it at this for now. This was a pretty cool problem. I really like binary tree problems. And yeah, hope you enjoyed the video, and I'll see you next time. Bye.